Hello. Welcome back. Wherever you are tonight, and I find myself genuinely wondering, at this hour, what particular corner of the world you've settled into, what quality of light is falling across the room, whether there's a specific sound outside that tells you exactly where you are without needing to open your eyes. I'm glad you're here. This is a good hour to have arrived at. Whatever brought you here tonight, you've made a good choice. Go ahead and settle in properly. Not the tentative kind of settling that's still half listening for one more thing to happen. The complete kind. Let your weight become entirely real against whatever is holding it up. Let your shoulders finally set down whatever they've been carrying since this morning. Let your breathing find its own unmanaged rhythm. You don't need to hold on to anything tonight. What stays with you will stay because it found something in you already waiting for it. The rest will simply drift past, and that's exactly as it should be. This isn't a test. It's a long, slow unspooling of something true, offered at whatever pace lets your eyes close on their own. If you're new here, welcome. This is Late Space, and what we do is take the largest ideas we can find and slow them down until they fit the shape of a quiet evening. If this feels like somewhere you'd like to return to, a gentle like or subscribe helps other people find their way here too, on their own restless nights. But that's for later, for the more awake hours. Right now, there's only this. Tonight, we're going to talk about the nearest star system to our own. The one that, for as long as human beings have looked up and wondered whether there was anyone else out there, has occupied a very particular place in our imagination. Not because it's especially different from the billions of other stars scattered across the galaxy, but because of a single, simple fact. It's close, closer than anything else. The nearest neighbour we have, in a universe otherwise defined by distances too vast to properly hold in the mind. Alpha Centauri. And I want to tell you, gently, honestly, at the pace this deserves, about a truth regarding that system that is not often discussed in the breathless, optimistic language that usually surrounds it. A truth that isn't dramatic in the way of danger or disaster, but that is, in its own quiet way, genuinely difficult to sit with. Disturbing, even, if you let it fully land, not because anything is wrong with Alpha Centauri itself, but because of what it reveals about the actual physical relationship between our species and the stars we have always dreamed of reaching. Here is the truth, stated as plainly as I can state it, before we spend the rest of tonight understanding exactly what it means. Alpha Centauri holds right now, tonight, a confirmed Earth mass planet sitting in its star's habitable zone, a genuine, real candidate for a world that might, in some form, support life. It is only 4.2 light-years away, which sounds, when you say it quickly, almost within reach. And the single most serious, most carefully funded, most scientifically credible plan humanity has ever developed for actually travelling there. A plan backed by $100 million. By some of the most brilliant engineering and physics minds of our generation, by the late Stephen Hawking himself, has, within the last year, quietly, almost silently, collapsed. The nearest world that might host life has never been closer to our instruments, and never farther from our reach. We're going to sit with that tonight. Slowly, carefully, not to frighten you and not to leave you in despair, but because I think there is something genuinely important, genuinely clarifying, in understanding exactly what stands between us and the stars, and in understanding, too, what remains true and beautiful even once we've looked that difficulty fully in the face. Close your eyes when you want to. Let's begin. Let's start with the system itself, because before we can understand the disturbance in this story, we need to properly understand what's actually there, what we've found, and how remarkable it genuinely is. Alpha Centauri is not a single star. It's a system of 3, bound together by gravity, drifting through the galaxy as a small family rather than a lone traveller. Two of these stars, Alpha Centauri A and Alpha Centauri B, are Sun-like stars, orbiting each other in a close binary pair, close that is by stellar standards. Though the actual distance between them varies over their 80-year orbital dance from roughly the distance between our Sun and Saturn, at their closest approach, to roughly the distance between our Sun and Pluto, at their farthest. The third member of this family, Proxima Centauri, is a much smaller, much dimmer red dwarf star, orbiting the central binary pair from a considerable distance, so far out that its own orbital period around its two larger companions is measured not in decades but in hundreds of thousands of years. Proxima Centauri, despite being the faintest and least dramatic of the three stars, happens to be the closest individual star to our own Sun, which is why when people speak casually about the nearest star, they are usually, whether they realise it or not, speaking about Proxima. And around Proxima Centauri, astronomers have confirmed the existence of a planet, Proxima Centauri b. Discovered in 2016, this world has a mass remarkably close to Earth's own, not identical, but genuinely comparable, genuinely rocky, genuinely the right general size and mass category to be called Earth-like in the most literal sense of that phrase. And crucially, it orbits its star at exactly the distance where, given the right atmospheric conditions, liquid water could plausibly exist on its surface. It sits, in other words, squarely within what astronomers call the habitable zone, the narrow, precious band of orbital distance, where a planet is neither too close to its star to have every drop of water boiled away, nor too far to have every drop of water frozen solid. This is not a small thing. Of all the thousands of exoplanets astronomers have discovered scattered across the galaxy, very few are both roughly Earth size and sitting in their star's habitable zone. And of that very small number, none, not one, is closer to us than Proxima Centauri b. The nearest star to our Sun has a planet that might, genuinely, plausibly, actually be habitable. And it is 4.2 light-years away. Let me try to help you feel what 4.2 light-years actually means, because I think this is where tonight's story really begins to acquire its particular, quiet weight. A light-year is the distance light travels in a single year, moving at roughly 186,000 miles every single second, the fastest speed anything in the universe is capable of reaching. In 1 year, moving at that almost incomprehensible pace, light covers approximately 6 trillion miles. 4.2 light-years, then, is a distance of roughly 25 trillion miles. 25 trillion. It's the kind of number that, spoken aloud, simply slides past the mind without really landing, the way very large numbers so often do. So let's try, instead, to feel it through comparison, the way we've done together on other nights here. The fastest spacecraft humanity has ever built and launched, Voyager 1, the extraordinary little probe that left Earth in 1977 and has been travelling outward, faithfully, for nearly 50 years now, moves at roughly 17 kilometers per second. It is, right now, tonight, the single fastest human-made object ever to exist, farther from Earth than anything else we've ever built. If Voyager 1 were somehow redirected, right now, tonight, toward Alpha Centauri, which it isn't, its trajectory carries it nowhere near that system. But let's imagine it for a moment. Purely for the sake of feeling this distance properly, the journey would take approximately 75,000 years. 75,000 years is more than 10 times longer than the entirety of recorded human history. It is a span of time so large that if you tried to walk it backward from today, you would pass through every empire, every written language, every city ever built, and you would still not have reached the beginning of that journey. You would still be walking deeper and deeper into a past before agriculture, before settled human communities of any kind, into an era when our species was still small bands of hunter-gatherers, moving across a world that had not yet been mapped, named, or written about in any form that survives to us today. That is the scale of the gap between us and the nearest potentially habitable world in the universe, not measured in miles, which is too abstract to feel, but measured in the actual physical time it would take our fastest existing technology to cross it. The nearest world that might host life sits at a distance that our fastest machine, moving as fast as anything we have ever built has ever moved, would need 75,000 years to reach. Wherever you are, I hope you're comfortable. Let's breathe here for a moment before we go further, because I want that number to have time to properly settle before we move on to the next part of tonight's story, the part that makes this whole situation feel, I think, genuinely disturbing in a way that goes beyond simple distance. Because here is the thing, 75,000 years at Voyager's speed is not actually the end of the story. It's the beginning of it. Because Voyager, remarkable as it is, was never designed for interstellar travel. It was built to visit the planets of our own solar system, and its speed reflects that comparatively modest ambition. If humanity genuinely wanted to reach Alpha Centauri, not in 75,000 years, but within something closer to a human lifetime, within a time frame that might actually mean something to the people who launched the mission, we would need something dramatically, almost unimaginably faster. And astonishingly, remarkably, we did have a plan for exactly that. A real one. Not a fantasy, not idle speculation, but a genuine, carefully engineered, seriously funded scientific and technological program designed by some of the most capable minds of our generation, aimed directly and specifically at making a journey to Alpha Centauri achievable within a human lifetime. It was called Breakthrough Starshot. Let me tell you the story of this project properly, because I think it deserves to be told with real care, both for what it attempted and for what ultimately happened to it. Because the story of Breakthrough Starshot is, in many ways, the beating heart of tonight's entire conversation. In 2016, the Russian-Israeli entrepreneur and physicist Yuri Milner announced the formation of Breakthrough Starshot, backed by $100 million in seed funding and guided by an extraordinary scientific advisory board that included, among others, the late Stephen Hawking, the astronaut and physician Mae Jemison, the former director of NASA's Ames Research Center Pete Worden, and leading astronomers from Harvard, MIT, and Carnegie Mellon. The concept at the heart of Starshot was genuinely, beautifully audacious, and I want to walk you through it slowly. Because understanding exactly how it was supposed to work makes what happened to it all the more poignant. Rather than trying to build a large, heavy spacecraft and accelerate it using conventional rocket propulsion, an approach that, as we've discussed in previous conversations here at Late Space, runs quickly and mercilessly into the brutal mathematics of the rocket equation, where every bit of additional speed requires disproportionately, exponentially more fuel. Starshot proposed something radically different. Build, instead, an extraordinarily small spacecraft. Not small in the sense of modest, but small in the sense of almost impossibly minuscule. A chip, roughly the size of a postage stamp, weighing perhaps a single gram, carrying tiny cameras, sensors, and a communication system, all miniaturized down to the absolute physical limits of what modern engineering could achieve. Attach this tiny chip to an equally tiny, ultra-thin, ultra-reflective sail, only a few meters across but weighing next to nothing. Then, rather than carrying fuel aboard the spacecraft itself, push it from Earth. Build an enormous array of ground-based lasers. Starshot's design called for something in the range of 100 gigawatts of combined power. An amount of energy that dwarfs almost anything humanity has ever concentrated into a single coordinated beam. Fire this extraordinary concentration of laser light at the tiny reflective sail for a matter of minutes. The photons themselves, carrying momentum even though they have no mass, would push against the sail exactly the way wind pushes against the sail of a boat, accelerating the featherlight spacecraft to speeds that no chemical rocket could ever hope to achieve. According to Starshot's original design, this brief but immensely powerful laser pulse would be enough to accelerate the tiny spacecraft to roughly 20% of the speed of light within about 10 minutes, reaching, in that short span, a velocity that would carry it halfway to Mars before the day was even over. At that speed, 1/5 the speed of light itself, the journey to Alpha Centauri, that same 25 trillion mile gulf that would take Voyager 75,000 years to cross, would take approximately 20 years. 20 years. Not 75,000. 20. A span of time that fits comfortably, achievably, meaningfully within a single human lifetime, a mission that a person could reasonably launch in their 30s and hope to see the results of before they reached old age. A genuine, serious, scientifically grounded plan to send humanity's first true emissary to another star within the lifetime of the people who built it. I want you to sit with that vision for a moment, because I think it's genuinely one of the more beautiful things our species has ever seriously proposed, and I don't want it to be lost or diminished by what I'm about to tell you next. Imagine it properly. A vast array of lasers built somewhere in a high-altitude desert with exceptionally clear, stable air. The Atacama Desert in Chile has been discussed as a leading candidate site, chosen for precisely the same reasons that make it home to some of the world's most powerful ground-based telescopes. A coordinated pulse of light, more concentrated and more powerful than almost anything ever produced by human hands, launched skyward for a matter of minutes. A spacecraft smaller than your hand, carrying within its tiny frame a camera, a communication system, and whatever scientific instruments could be miniaturized to fit, accelerating faster and faster until it was moving at 1/5 the speed of light, fast enough to cross the entire distance from the Earth to the Moon in about a second and a half. And then, 20 years later, 2 decades of patient, faithful waiting, the mission team growing older, some of the original scientists perhaps retiring, perhaps passing the project on to younger colleagues who weren't even born when the laser first fired, a signal arriving back at Earth. Faint, delayed by another 4 years simply for the light itself to make the return journey. But real. The first images ever of another star system captured up close by an instrument built and launched by human hands. This was not science fiction. This was an actual, funded, seriously pursued engineering program with real physicists working through real technical problems in the years following 2016. And in 2025, as best as careful investigative reporting has been able to determine, it quietly, almost silently came apart. Let me tell you what happened, as honestly and as carefully as the available reporting allows, because I think the manner of this project's ending is, in its own way, as instructive as its original, beautiful ambition. According to detailed investigative reporting published in Scientific American in 2025, Breakthrough Starshot, despite its original $100 million commitment, had by that point actually spent only about $4.5 million spread across roughly 30 separate research contracts over the course of nearly a decade. No working prototype of any of the mission's core subsystems, not the laser array, not the light sail, not the miniaturized spacecraft itself, had been produced. When journalists attempted to reach the project's key figures, including Pete Worden and the physicist Avi Loeb of Harvard, both had declined to be interviewed. A representative for the Breakthrough Prize Foundation had indicated that a comprehensive report on the project's status would be released in the spring of 2025. That report never appeared. As the Scientific American piece put it, with a particular, quiet bluntness that I find worth repeating exactly, at this stage the future of the program is murky. Starshot appears to be on indefinite hold, if not over, although there was no final announcement and no fanfare to match its beginnings. I want to sit with that phrase for a moment, because I think it captures something genuinely poignant about how this particular story ended. There was no dramatic cancellation, no press conference announcing failure, no formal acknowledgement that the most serious, most carefully considered plan our species had ever developed for reaching another star had, quietly, without ceremony, stopped moving forward. It simply, gradually, went still. The funding slowed. The updates stopped. The key figures declined interviews. A promised report never materialized. And somewhere in that quiet accumulation of silence, one of humanity's most beautiful ambitions came to rest, unfinished, unexplained, and largely unnoticed by the wider world. This, I think, is the first genuinely disturbing truth we need to sit with tonight. Not that interstellar travel is difficult, we already knew that, in the abstract, the way we know many difficult things without fully feeling their weight. The disturbing part is watching, in close to real time, what actually happens when even the most serious, most well-funded, most brilliant attempt to solve that difficulty runs up against the genuine scale of the problem. It doesn't fail with drama. It doesn't fail with a clear, decisive negative result that at least offers the clean satisfaction of a definite answer. It simply, slowly, quietly, stops. Wherever you are, I hope you're still comfortable. I know this is a heavier note than we sometimes strike here at Late Space, and I want to honour that, rather than rushing past it toward easy comfort. Let's stay with it a little longer, because I think there's more here worth understanding before we can properly, honestly arrive at something more hopeful. Why specifically did Starshot struggle the way it did? What actually stands between the beautiful vision I described a few minutes ago and its realization? The honest answer involves several genuinely difficult, currently unsolved engineering problems, each significant enough on its own to represent a serious scientific challenge, and all of which needed to be solved simultaneously for the mission to work at all. The laser array itself, that 100-gigawatt coordinated pulse of light, represents an engineering challenge of a scale that has, quite simply, never been attempted. Building and precisely coordinating an array of lasers powerful enough, and capable of maintaining that power in a tight, stable beam across the vast distance needed to accelerate a tiny sail to a meaningful fraction of light speed, pushes considerably beyond the current state of laser technology, requiring advances in power generation in beam coherence. And in atmospheric compensation that remain, as of today unsolved, the sail itself must be simultaneously almost impossibly thin and light. Thin enough that the tiny craft's total mass remains low enough for the laser's push to actually achieve meaningful acceleration, while also being robust enough to survive that acceleration without tearing, warping, or melting under the intense concentrated energy of the laser pulse itself. And then, once the tiny craft is actually moving at 1/5 the speed of light, coasting silently through interstellar space for 2 decades, it faces a genuinely severe and often underappreciated hazard: interstellar dust. At such extraordinary velocities, even a single grain of dust, no larger than a speck barely visible to the naked eye, carries enough kinetic energy on impact to seriously damage or entirely destroy a spacecraft this fragile. Starshot's original design accounted for this by planning to launch not one spacecraft, but potentially thousands of them simultaneously, a swarm rather than a single probe, on the assumption that only a fraction would likely survive the full 20-year transit intact. And even for the survivors that do make it all the way to Alpha Centauri, moving at 1/5 the speed of light, there is no plan, none, in any current design to actually slow down. The spacecraft would not orbit the system, would not settle into a stable position for extended observation. It would simply fly through at tremendous speed, capturing whatever images and data it could during a flyby, lasting perhaps only a few hours, before continuing onward forever into the depths of interstellar space beyond. Each of these challenges, on its own, represents a genuinely serious, unsolved problem in modern physics and engineering. Together, pursued simultaneously by a project operating on a fraction of its promised funding, they proved, at least for now, to be more than the current effort could overcome. I want to be careful here, because I don't want tonight's conversation to leave you with the impression that interstellar travel is simply, permanently impossible. Because that isn't quite accurate either. And I think the more honest, more useful truth lies somewhere more nuanced than either easy optimism or flat despair. Breakthrough Starshot's difficulties don't represent a fundamental violation of physics. Nothing about the plan requires technology that breaks any known law of nature. Every individual piece of the puzzle, powerful lasers, ultralight reflective sails, miniaturized electronics, dust shielding, represents, in principle, an achievable engineering goal. Something that future advances in materials science, in laser technology, in miniaturization could plausibly solve, given enough time, enough investment, and enough sustained scientific attention. What Starshot's quiet stall actually reveals, I think, is something more subtle and, in its own way, more genuinely worth sitting with. The gap between what is theoretically possible and what a specific effort, operating with specific resources over a specific span of years, can actually accomplish in practice. The physics remain sound. The engineering challenges remain, in principle, solvable, but solving them requires a sustained, well-resourced, patient, multi-decade commitment that, for reasons involving funding, focus, institutional continuity, and simple human attention span, this particular effort was ultimately unable to maintain. This is, I think, one of the genuinely important, genuinely disturbing truths worth sitting with tonight. Not that the stars are permanently and physically unreachable, but that reaching them requires a form of sustained collective human commitment that we have, so far, struggled to maintain across the multi-decade timescales the challenge actually demands. The barrier isn't only physics, it's also, quietly, us, our attention, our patience, our capacity to fund and sustain and pass forward a project whose payoff might not arrive within the working lifetime of the people who begin it. Let's turn now to the other half of tonight's story, because there is more happening in the Alpha Centauri system right now than the quiet collapse of Starshot, and some of it is genuinely, remarkably hopeful, even as it carries its own particular strangeness. While the propulsion side of this story has stalled, the observational side, our ability to actually see, to actually detect and characterize what exists in the Alpha Centauri system, has been advancing in genuinely extraordinary ways, driven largely by the James Webb Space Telescope. Let me tell you first about Proxima Centauri b, that confirmed Earth-mass world in the habitable zone, because there has been real, encouraging news about it recently. In May 2026, a research team published a study finding evidence suggesting that Proxima b may possess a magnetic field. This matters enormously for the question of habitability, because on Earth, our planet's magnetic field plays a crucial protective role, helping shield our atmosphere from being gradually stripped away by the constant stream of charged particles flowing outward from the Sun. Without Earth's magnetic field, our atmosphere, and with it, our oceans, and with them, quite possibly, the entire foundation of life as we know it, would likely have been eroded away by solar radiation over the course of billions of years. If Proxima b has a genuine magnetic field of its own, this substantially increases the odds that it has managed to retain a meaningful atmosphere, despite orbiting extremely close to its host star, Proxima Centauri, being a small, dim red dwarf, requires its habitable zone to sit unusually close to the star itself, well within the kind of distance where intense stellar activity might otherwise be expected to strip a planet bare. I want to be honest and careful here, the way we always try to be honest and careful in these conversations, because Proxima b's habitability remains genuinely, seriously debated among scientists. This new evidence of a possible magnetic field is encouraging, but it is not, on its own proof of a breathable atmosphere, liquid water, or anything resembling life. It is one hopeful data point in an ongoing, careful, still unresolved scientific investigation. But it is a genuinely hopeful one, and it deserves to be held, gently, alongside everything else we're discussing tonight. And then there is a stranger, more elusive story unfolding around the other two stars in the system, Alpha Centauri A and Alpha Centauri B, the Sun-like binary pair at the system's heart. In August 2024, the James Webb Space Telescope, using an extraordinarily sensitive technique called coronagraph imaging essentially, physically blocking out the overwhelming glare of a star's own light, in order to have any hope of glimpsing something as comparatively faint as an orbiting planet, captured what appeared to be a genuine planetary candidate near Alpha Centauri A. This detection was, on its own, remarkable enough. Sun-like stars like Alpha Centauri A are notoriously difficult targets for direct planetary imaging, precisely because their light is so much brighter than any planet that might be orbiting them, making the kind of faint signal astronomers were looking for extraordinarily easy to lose within the star's own overwhelming glow. But then something strange happened. When the research team returned to observe the system again, in two separate follow-up campaigns conducted in February and April of 2025, the candidate planet, which the team had informally designated S1, was nowhere to be found. It had, quite simply, vanished from the instrument that had originally detected it. This could, on its own, have meant that the original 2024 detection was simply an error, an instrumental artifact, a background object masquerading as a planet, a trick of processing rather than a genuine discovery. This is, in fact, exactly the kind of possibility that careful, responsible scientists are obligated to rule out before claiming any real discovery. And the research team did exactly that kind of rigorous, careful checking, conducting extensive tests to confirm that the original signal wasn't simply an instrument glitch or a distant background galaxy being mistaken for something closer and smaller. But instead of concluding that S1 wasn't real, the team pursued a different, more patient explanation. Using sophisticated computer modelling, they simulated millions of potential orbital paths the candidate planet might be following around Alpha Centauri A, testing which of those millions of possible orbits would be consistent with the planet being visible in the original 2024 observation, and then invisible, hidden, effectively, by its own orbital motion. Swinging behind the glare of its star or into a position where Webb's specific imaging technique simply couldn't distinguish it, during both of the 2025 follow-up attempts. The result of this careful modelling was genuinely striking. 52% of all the physically possible stable orbits the researchers tested were fully consistent with exactly this pattern. A planet that had genuinely been present and detectable in 2024, and that had then, through the entirely ordinary, entirely expected physics of orbital motion, simply moved into a position where it became temporarily undetectable in both subsequent observation windows. In other words, the leading, best-supported current explanation is not that S1 was a fluke or an error. It's that S1 is very likely real, a genuine planet, quite possibly a gas giant roughly the mass of Saturn, orbiting Alpha Centauri A at a distance of roughly twice the separation between our own Sun and Earth, and that it has simply been playing an extraordinarily patient game of astronomical hide-and-seek with the most sophisticated space telescope our species has ever built. Wherever you are, I hope you're comfortable. I want to sit with this particular detail for a moment, because I find something genuinely, quietly moving in it. A small, specific illustration of exactly the kind of patient, careful, humble work that real science actually requires, especially when reaching towards something as distant and as difficult as another star system. Imagine the researchers on that team having captured what genuinely looked like a real planetary detection, returning eagerly to confirm it, and finding nothing. No signal, no trace. The kind of result that could, understandably, be read as failure as evidence that the original excitement had been premature, that there was nothing there after all, and instead of abandoning the finding, instead of quietly filing it away as an error, the team chose the harder, more patient path, building an enormous simulation, testing millions of possible explanations, searching carefully for whether the absence of a signal might itself be consistent with, rather than contradictory to, the presence of something real. Following the actual physics of orbital motion to its logical conclusion, rather than simply accepting the first, easiest interpretation of an ambiguous result. This is, I think, a genuinely beautiful example of what patient, honest science actually looks like from the inside. Not a triumphant, dramatic discovery announced with total confidence in a single moment, but a careful, humble, ongoing process of testing, retesting, and gradually building confidence in something that remains, even now, not fully, completely confirmed. As one of the researchers involved, Caltech doctoral student Aniket Sanghi noted in discussing the finding, the very existence of a planet in a system with two closely separated stars would challenge our current understanding of how planets manage to form, survive, and evolve in such gravitationally chaotic environments. If S is real, and the evidence increasingly suggests it likely is, it would represent not just a new world discovered, but a genuine puzzle for planetary science, a system that appears to be quietly defying some of our existing assumptions about where and how planets are able to take shape. Let's bring these two threads together now, the quiet collapse of Breakthrough Starshot, and the patient, ongoing, genuinely remarkable work of actually detecting and characterizing what exists in the Alpha Centauri system, because I think their combination is exactly what gives tonight's disturbing truth its particular, distinctive shape. We are getting better, faster, more sophisticated at seeing. The James Webb Space Telescope, an instrument that didn't even exist a decade ago, has already detected a possible magnetic field around Proxima b, has glimpsed and then patiently tracked down strong evidence for an entirely new planet around Alpha Centauri A, and continues through 2025 and into 2026 its careful, ongoing campaign of observation across this entire nearby system. Our ability to characterize, from a distance of 25 trillion miles, the atmospheric composition, the magnetic properties, the very existence of worlds we cannot visit, is advancing in genuinely extraordinary ways. And simultaneously, our ability to actually go there, to physically cross that same 25 trillion miles, to send something, anything, human-built, human-designed, to actually arrive at these worlds we're growing steadily more capable of studying from a distance, has, at least for now, quietly stalled. This is the disturbing truth at the heart of tonight's conversation. Not that Alpha Centauri is unreachable in some permanent, absolute sense, but that we currently find ourselves in a genuinely strange, genuinely uncomfortable position, capable of seeing, in remarkable and increasing detail, exactly what we're missing, while our capacity to actually close that distance remains stalled, underfunded, and quietly adrift. We can see the shore. We have built, with extraordinary care and ingenuity, instruments capable of making out its details from an almost unimaginable distance. And the boat we built to actually sail there sits unfinished, in dry dock, its construction quietly, gradually abandoned. I want to spend some time now, gently, with what this actually means, not just as a fact to note and move past, but as something worth genuinely feeling, here, at this hour, in this particular quiet. There is a specific kind of ache in knowing exactly what you're missing. It's different from simple ignorance, from not knowing what lies beyond your reach. If we had no idea whether Alpha Centauri held any habitable worlds at all, if the system remained, as it did for most of human history, simply 3 points of light in the night sky, their planetary contents entirely unknown, there would be a kind of mercy in that uncertainty. You cannot properly long for what you cannot properly imagine. But we do know, now we know there is a world, Earth mass, sitting in its star's habitable zone, possibly shielded by its own magnetic field, possibly capable of holding on to liquid water, possibly, genuinely, scientifically possibly, capable of supporting some form of life. We know there is very likely another planet, a gas giant, orbiting the system's other sun-like star, defying our expectations about how planets can form in such chaotic, closely spaced binary environments. We are learning more about these worlds, in increasing and genuinely remarkable detail, with each passing observational campaign. And we cannot go there. Not within any time frame that connects meaningfully to a human life, a human institution, a human civilization as currently organized. The one serious plan we had for closing that gap within a human lifetime has, for now, quietly stalled. This is worth sitting with honestly, I think, rather than rushing past toward easy comfort. There is something genuinely disturbing, genuinely difficult, in this particular configuration of knowledge and inability, in knowing, with increasing precision, exactly what we're reaching for, while watching our capacity to actually reach it falter. And yet, I want to offer you something else now, something that doesn't erase or dismiss everything we've just discussed, but that sits alongside it, because I think it's equally true, and because I think it's the more important note to carry with you towards sleep tonight. The distance between us and Alpha Centauri has not changed. It remains exactly what it has always been, 25 trillion miles, 4.2 light years, a gap that light itself requires more than 4 years to cross. What has changed, dramatically, remarkably, within just the past decade, is how much we know about what actually lies on the other side of that gap. 10 years ago, before Proxima B's discovery in 2016, we didn't know whether the nearest star system held any planets at all worth caring about. We were reaching, in a very real sense, into the dark, hoping rather than knowing. Today we know there is a confirmed Earth-mass world in a habitable orbit, possibly protected by a magnetic field. We have strong, carefully modelled evidence for an entirely separate planet orbiting the system's other sun-like star. We have an instrument, Webb, actively, patiently, continuing to study this system in ever-increasing detail, with additional observation campaigns already conducted and more surely to come. This represents genuinely one of the most remarkable expansions of human knowledge in recent memory, not because we've solved the problem of actually travelling there, but because we've transformed our relationship with this system from one of pure speculation into one of increasingly detailed, increasingly confident scientific understanding. We are not merely dreaming about Alpha Centauri anymore. We are studying it, characterizing it, building, patiently, piece by careful piece, an actual, evidence-based picture of what these worlds are genuinely like. And the propulsion problem, difficult and currently stalled as it is, remains, as we discussed earlier, a problem of engineering and sustained commitment rather than a fundamental violation of physics. The laser array Starshot envisioned has not been built, but nothing about the underlying physics has been disproven. The technical challenges, beam coherence, sail durability, dust shielding, deceleration at the destination remain difficult, but they remain in principle solvable, given the kind of patient, sustained, well-resourced effort that this particular attempt was ultimately unable to maintain. Wherever you are, I hope you're still comfortable. I want to tell you about one more piece of this story, because I think it offers a genuinely useful, genuinely grounding perspective on how to hold everything we've discussed so far tonight. There is another, considerably slower, considerably less dramatic proposal for eventually reaching Alpha Centauri that has continued to be developed and refined, even as Starshot's more ambitious timeline has stalled. It's called Chrysalis, and rather than attempting the extraordinary speed and extraordinary miniaturization that Starshot required, it proposes something almost entirely opposite in character: a vast, self-sustaining, city-sized generation ship carrying more than 1,000 people, designed to make the journey to Alpha Centauri not in 20 years, but in something closer to 400. 400 years is a genuinely staggering span of time to hold in mind for a single continuous mission, far longer than the entire history of the United States, longer than the time separating us from the earliest European settlements in the Americas. A ship launched under Chrysalis's design would need to sustain, across multiple human generations, an entirely self-contained civilization, growing its own food, recycling its own air and water, educating its own children, maintaining its own social and technical institutions, all while carrying forward, faithfully across 16 or more generations, the original mission and purpose that the very first travellers set out with. I mention Chrysalis not because it represents an easier or more immediately practical path than Starshot's laser sails. If anything, the challenges of maintaining a genuinely self-sustaining multi-generational human society for 4 centuries are, in their own way, at least as difficult as the physics of laser propulsion, if not considerably more so. I mention it because it represents a genuinely different way of thinking about the relationship between human ambition and cosmic distance. Starshot's approach was to bend the mission to fit within a single human lifetime, to make the journey fast enough that the people who began it could reasonably hope to see, or at least hear about, its conclusion. Chrysalis's approach is almost the opposite: to accept that some journeys are simply larger than any single human life, and to design instead for continuity across generations, for a form of collective, sustained, patient human commitment that doesn't require any single person to personally witness the ending. Both approaches, I think, reveal something important about what reaching the stars will actually require of us, whichever specific technical path eventually succeeds. It will require either extraordinary technological breakthroughs, sustained patiently across decades of committed effort, or it will require an entirely different relationship with time itself, a willingness to begin something. Carefully, honestly, knowing you will not personally see its end, trusting that those who come after you will carry it forward with the same care you brought to its beginning. I want to bring this back now to something more immediate, more personal, because I think this is where tonight's conversation genuinely belongs, not just in the abstract physics of laser sails and orbital mechanics, but in what all of this means for you, here, tonight, thinking about these vast distances from the comfort of wherever you're resting. The disturbing truth about travelling to Alpha Centauri at its heart is really a truth about time, about the profound, sometimes uncomfortable gap between what a single human lifetime can accomplish and what the universe, at its actual physical scale, actually requires. You will very likely not see a human being or even a human-built spacecraft arrive at Alpha Centauri within your lifetime. This is, I think, simply honestly true, and there's no real use in pretending otherwise. The propulsion technology required doesn't yet exist in working form. The one serious, well-funded attempt to build it has quietly stalled. Even if a renewed, better-resourced effort began tomorrow, the engineering challenges involved would likely require decades of patient, sustained development before any actual launch became possible, and decades more at minimum for the journey itself. And yet, I want you to notice something about how this particular kind of disappointment differs from other, more ordinary disappointments in life. This is not a failure of your own effort, your own choices, your own capacity to achieve something you personally set out to do. This is simply, honestly, a reflection of where our species currently stands in an extraordinarily long, extraordinarily patient, multi-generational project. The project of actually reaching beyond our own solar system, of extending human presence, human knowledge, human curiosity, out into the wider galaxy. You are not failing to reach Alpha Centauri. You are living during one particular, early chapter of a story that will very likely take many more generations to fully unfold. A story in which the specific, careful, patient work being done right now, in 2026, by researchers modelling millions of possible orbits, by engineers slowly refining laser and sail technology, by scientists patiently, carefully building an ever more detailed picture of what actually exists around those 3 distant nearby stars, represents genuine, real progress, even though it hasn't yet, and may not for a very long time, culminate in an actual human arrival. Let me offer you one final way of thinking about all of this, before we begin the slow descent towards sleep, because I think it's the frame I most want you to carry forward from tonight. Every single scientific and technological achievement our species has ever accomplished, every telescope, every spacecraft, every careful theory, patiently tested and refined across generations, has been built by people who inherited an unfinished project from those who came before them, and who in turn left that project unfinished for those who would come after. The astronomers who first identified Alpha Centauri as a nearby star system centuries ago, using nothing more than careful, patient, naked eye, and early telescopic observation, could never have imagined the James Webb Space Telescope or coronagraph imaging, or the specific remarkable technique of modelling millions of possible orbits to hunt for a hidden planet's most probable path. They simply did the careful, patient work available to them, in their own moment, and passed forward what they learned. The physicists and engineers who conceived of Breakthrough Starshot in 2016, and who have spent the years since carefully, patiently working through some of its most difficult technical challenges, even as the project's broader momentum has stalled, have nonetheless generated real, genuine scientific and engineering knowledge about ultralight sail materials, about laser array physics, about the specific hazards of interstellar dust at relativistic speeds. That knowledge does not simply disappear because the project's original, ambitious timeline has quietly stalled. It remains patiently, waiting to be picked up again, refined further, eventually incorporated into whatever future effort finally succeeds in solving the problems this particular attempt could not fully overcome. You tonight lying here, having taken the time to properly understand this whole difficult, beautiful, genuinely disturbing story, you are, in your own small way, part of that same long chain. Not because you're building anything, or funding anything, or personally advancing the science, but because understanding, properly, honestly, the genuine scale and genuine difficulty of what we're attempting is itself a form of keeping faith with the project, a way of honouring both the extraordinary work already done and the extraordinary work still required, without flinching from either the difficulty or the beauty of what's actually at stake. Let's come down now, slowly, gently, toward the end of tonight's long conversation. Here is what is true, as carefully and as honestly as I can leave it with you. Alpha Centauri, the nearest star system to our own, holds a confirmed Earth-mass planet sitting in its star's habitable zone, Proxima Centauri b, along with growing, genuinely encouraging evidence, as of May 2026, that this world may possess its own protective magnetic field. The system's other 2 stars, Alpha Centauri A and B, likely host at least one additional planet, a probable gas giant that has been patiently, carefully tracked through a combination of direct observation and sophisticated orbital modelling, even as it plays its own extraordinarily patient game of hide and seek. With our most powerful space telescope, the single most serious, most carefully engineered plan for actually reaching this system within a human lifetime, Breakthrough Starshot, backed by $100 million and some of the finest scientific minds of our generation, has, as of 2025, quietly, without fanfare, stalled, having spent only a small fraction of its promised funding and produced no working prototype of its core. Technologies. At the speed of our fastest existing spacecraft, the journey would take 75,000 years. At the speed Starshot once hoped to achieve, it could take 20. Right now, tonight, neither timeline represents a genuinely active, moving mission. This is the disturbing truth. Not that the stars are forever, permanently unreachable. Nothing about the underlying physics forbids it. But that the actual, sustained, multi-decade human commitment required to close this particular gap has, for now, faltered. Even as our capacity to see, to study, to understand what lies on the other side of that gap continues to advance in genuinely remarkable ways. We can see the shore with ever-increasing clarity. The boat remains, for now, unfinished. I want to leave you with one final image before we close, because I think it captures, better than any summary I could offer, the particular texture of feeling I hope you carry with you into sleep tonight. Imagine, if you can, that faint point of light in the southern sky, Alpha Centauri, visible, on a clear night from the right latitude, as one of the brightest stars overhead, though from where most of you are listening tonight. In the northern hemisphere, it likely sits below your horizon, invisible, its light travelling toward a part of the world where someone else right now might be looking up and seeing it. That light left its source 4.2 years ago. Whatever you would see, if you could see it tonight, is not what Alpha Centauri looks like right now, in this present moment. It's what it looked like 4 years in the past. The light having travelled all this way, faithfully, patiently, at the fastest speed anything in the universe is capable of achieving, simply to reach your eyes tonight. Somewhere within that light, encoded in ways our instruments are only beginning to properly decode, is information about a planet that may have its own magnetic field, its own protective shield against the harsh radiation of its small dim star. About another planet, a gas giant, quietly, faithfully completing its own long orbit around a sun-like star not so different from our own. We cannot go there yet. Not within any timeline that connects meaningfully to a single human life. But we are, patiently, carefully, generation by generation, learning to read that light more clearly than any humans before us ever have. And somewhere, in some future decade or century, the patient accumulation of that knowledge, combined with whatever renewed, better sustained effort eventually solves the propulsion problem that Starshot could not, will very likely someday close this gap entirely. You will very probably not see that day. And that is genuinely, honestly worth sitting with rather than glossing over. But you have tonight taken the time to understand exactly what stands between us and that day. The genuine physics, the genuine engineering, the genuine quiet human struggle to sustain a project larger than any single life. That understanding, held gently, honestly, without either false optimism or unnecessary despair, is itself a kind of quiet contribution to the whole long, patient, multi-generational project of actually, eventually, reaching the stars. Close your eyes if they're not already closed. Somewhere, tonight, beneath a different sky than the one above wherever you're resting, 3 stars are turning slowly through their long, patient orbital dance. 2 suns circling each other across decades, a smaller, dimmer companion circling them both across hundreds of thousands of years. Around one of them, a small, rocky, possibly magnetically shielded world completes its own tight, fast orbit, 4.2 light-years from where you're lying right now. We know it's there. We are learning, with each passing observational campaign, more about exactly what it's like. And the ship that might one day carry something of us there, whether a tiny laser-driven chip moving at 1/5 the speed of light, or a vast, patient, generation-spanning vessel carrying an entire small civilization across 4 centuries, remains, for now, unbuilt. That is the disturbing truth. And it is also held properly, gently at this hour, a genuinely beautiful one, because it means there is still, genuinely, something left for us to do. Something worth the patient, careful, generational effort of actually doing it. Thank you for spending tonight here. Thank you for sitting with something difficult, something honestly unresolved, and letting it be exactly as large and as complicated as it actually is. Sleep well. And somewhere 25 trillion miles away, the light of 3 distant suns keeps travelling toward us, faithfully, patiently, the way it always has. Good night.